Okay, good morning. Welcome to
KidMath number 89.
KidMath number 89. Okay, so what we've been talking about, this is the third movie in the series. In this short series, you had asked an interesting question about parabolas. So let's say this is y equals x squared, and it goes off to infinity. And you asked me, is there more area in here or out here? Which is a cool question. And you think the answer is?
They're equal.
They're equal because why?
When you extend them for infinity, this area is infinity and this area is infinity.
Right, so this area is infinite, this area is infinite. Now yesterday, we took a look at a triangular graph with lines with y equals absolute value of x. And we found that for any finite area, we drew a square. We had, if this area was, whatever, x, the area outside was 3 times as large, right?
Yeah.
So, and that got into the discussion of limits. And we showed our little calculus book. And did you read this yesterday and learn everything inside of it? And are you now completely fluent in calculus?
I think so.
Okay, good, because it's going to be a pain to teach anyway. Now, here's the next thing. To calculate, there's some easy stuff calculating the area outside of the parabola. Show me a place where it's easy to calculate the area.
Well, like at 0, 0, you could calculate an area.
Okay, what's the area of the point 0, 0?
I'm not sure. But squares are easy to calculate.
Okay, so we got like, if we draw the graph, we draw the axes and we got a nice little square here, and a nice little square here. Or a square-ish thing, right?
Yeah, but they go off to infinity too.
Yeah. But if we wanted to do what we did for y equals absolute value of x and draw a square like this.
We wouldn't have a triangle.
Right, we don't have a triangle on the inside, but this square would be easy. This square would be easy. This bit here and this bit here, which look like they're the same area, by the way, right?
Yeah, if this is like a perfect y equals x squared parabola.
Right. This we don't know how to calculate the area of yet. Is there an eraser? It's one of the best over there. So, that's what I want to talk about today. So this would no problem, this no problem, yeah, this up here, this in here, okay? But let's see. Let's see. Okay, so let's zoom in on our parabola. Okay, and let's say we were trying to find this area in here. And instead of having a triangle like we had yesterday, we have a curve. So what makes this difficult? What makes finding this area difficult?
This isn't if this was a straight line, like this.
Yeah.
It would be easier.
It'd be super easy, right? But if we approximated this with a straight line, then we are overestimating the area by a little bit. So how could I get a better approximation? You're right. I know how to find the area of triangles. It looks like I have a nice right triangle here, but it's not quite right. So how could I make it a little better? How could I get a better approximation than the triangle you drew?
Well, we could make a smaller triangle inside, but then we'd under-approximate.
Okay. Draw what you mean?
Like, maybe something like that.
Okay. And then maybe take the average of those?
Yeah, we'd leave off a little bit.
Okay, good. Do you have any other ideas on how we might find a good approximation? Because this is a problem that calculus deals with.
Not really.
Okay, well let me show you one idea then. What if I cut it in half? And I decided to approximate this point and then do something up here. Now this is sort of a rectangle and a triangle on top. But that's fine. I mean, I know how to do rectangles. I know how to do triangles. And this seems like it has less error.
Yeah.
Right? So I cut it in half and it looks like I get less error. What do you think the next step could be?
Cut it in half again.
Okay, draw that.
Like that.
Well, remember the curve is here.
Oh yeah.
Okay, so it's really down there.
Yeah. It's a little hard to draw.
But this is a great example of a math problem. And I don't want to get into a lot of the details, but the idea is we're trying to find this area here. We don't know how to find the area under curves. But we do know how to find the areas of triangles and rectangles. So what we want to do is try to chop this up into small things that we actually do know how to find the area of.
Like, these look like almost rectangles.
Yeah, in fact, we could use rectangles if we wanted to.
But then
Like
we have
that.
like these little,
Then we have these gaps, but then we just cut everything in half again.
and then we keep getting
and-
smaller and smaller and smaller.
Okay, and eventually, these rectangles will approximate what?
The area.
The area under the curve. And how many rectangles are we going to need to get it exactly right?
A lot. Probably infinity.
Infinity. Hey! So just like this goes all the way off to infinity, we're going to need an infinite number of rectangles to approximate here.
We need infinite rectangles to cover a finite area.
Yeah.
Interesting.
Yeah, that is interesting, isn't it? And actually, you want to see just for fun the mathematical symbol for this?
Yeah.
Okay. Let's say this is 0, and let's say this is 5, and this curve is y equals x squared. Okay.
Alright.
Mathematicians write the area here equals, this is called an integral from 0 to 5 of x squared dx. There's a new mathematical symbol for you. Now I'm just writing that down just because it's kind of cool looking, right?
Yeah.
Okay. So we'll talk about this a little bit more, probably 2 more days. Okay.
Okay.
All right. Good job, man. This is fun to talk about.